Imagine a mirror image of our universe where everything is flipped. This is the world of antimatter, a fascinating subject that challenges our understanding of existence. Antimatter, though it sounds like science fiction, is very real and holds keys to cosmic mysteries. Born with the Big Bang, antimatter is the perfect counterpart to matter, raising profound questions about the universe's composition. If matter and antimatter were equal, why is our universe dominated by matter? This puzzle drives much of today's research. Beyond cosmic scales, antimatter impacts our daily lives, especially in medicine, where it helps diagnose diseases and save lives. Antimatter is not just a concept for physicists, it's a tool for healing, showing how fundamental science benefits humanity. This journey into antimatter explores the fundamental nature of reality, its behavior, and its role in the universe's history. We will also see how we create and use it today as the story of antimatter continues to unfold with promises of future discoveries. Antimatter shapes our view of the cosmos and offers potential for future technologies we can only dream of now. What is antimatter? For every particle of matter, there is an antiparticle. Its antimatter twin, take an electron, a familiar particle with a negative charge. Its antiparticle, the positron, is almost identical but with a positive charge. This pattern holds for other particles too. Protons have antiprotons and neutrons have antineutrons, with differences deeper than just charge. When antiparticles combine, they form antimatter. An antiproton and a positron could form an antihydrogen atom, a mirror image of hydrogen. Scientists have created antihydrogen in labs, allowing us to study antimatter directly and test if its properties mirror matter as predicted. The idea of antimatter was first predicted by physicist Paul Dirac in the 1920s. His equations suggested these new particles. Initially, many were skeptical, but the discovery of the positron in 1932 confirmed Dirac's prediction, opening a new chapter in physics. Antimatter was shown to be a real part of our universe, not just a theoretical fancy. When antimatter meets matter, they annihilate each other, converting their mass into energy. This process, called annihilation, releases enormous energy, described by Einstein's equation mc2. Even a tiny amount of mass can be converted into a tremendous amount of energy, making annihilation the most efficient mass-to-energy conversion. Energy can also convert into matter and antimatter, showing the deep connection between them. This concept explains why antimatter is rare in our everyday experience. It quickly annihilates upon encountering matter. Scientists create antimatter in controlled environments, keeping it isolated from ordinary matter to study its properties. In the early universe, the Big Bang created a hot, dense environment where energy converted into particle-antiparticle pairs. These pairs annihilated back into energy, maintaining a balance of matter and antimatter. As the universe expanded and cooled, new pairs could no longer form, but annihilation continued. If matter and antimatter were perfectly equal, they should have annihilated completely, leaving a universe filled only with light. However, we live in a universe dominated by matter, suggesting a broken symmetry between matter and antimatter. The universe's matter dominance is a major mystery known as the problem of baryogenesis. Observations show a tiny asymmetry. For every billion antimatter particles, there was 1,000,000,001 matter particles. This small surplus of matter formed everything we see today, from atoms to galaxies. The cause of this imbalance is an unsolved problem in physics, with theories involving CP violation. CP violation means the laws of physics are not perfectly symmetrical when swapping particles with antiparticles and mirroring spatial coordinates. Experiments have observed CP violation, but not enough to explain the universe's imbalance. Scientists continue to search for answers, conducting experiments and exploring new particles and forces. Scientists create antimatter in specialized facilities using particle accelerators. These machines accelerate particles to high speeds, colliding them with targets to produce particle-antiparticle pairs. Antiprotons and positrons are created, the basic ingredients of antimatter. Once created, antiparticles are managed using magnetic and electric fields to separate and trap them. Trapping antimatter is challenging. It must not touch ordinary matter or it will annihilate. Sophisticated traps like penning traps hold antiparticles in a vacuum for study. Antimatter is used in positron emission tomography (PET) scans, a non-invasive diagnostic tool. PET scans help diagnose diseases by introducing a radioactive tracer that emits positrons into the body. Positrons quickly encounter electrons, annihilating and producing photons detected by the PT scanner. This process reveals areas of high metabolic activity, aiding in disease diagnosis and monitoring. Antimatter holds potential for propulsion and energy generation, with annihilation releasing immense energy. An antimatter-powered spacecraft could enable interstellar travel, and controlled annihilation could be a potent energy source. However, production and storage challenges make these applications currently impractical. Creating antimatter is inefficient, and storing it requires complex magnetic traps. Despite challenges, research continues exploring efficient production and niche applications. The perils of weaponizing antimatter are clear, but current capabilities are far from this reality. Antimatter's story continues from theoretical curiosity to experimental reality and tool for discovery. The matter-antimatter asymmetry remains a central focus, with experiments pushing boundaries. Scientists study anti-atoms, testing fundamental symmetries and searching for new physics. Each discovery adds to the cosmic puzzle, refining our models of reality. Antimatter inspires dreams of interstellar travel and challenges our brightest minds. Its journey from mathematical possibility to tangible substance is a testament to human ingenuity. The quest to understand antimatter is a quest to understand ourselves and our place in the cosmos.